Do you live in a smart home? If you do, you may be in the wrong video. My house is as dumb as they come, but there are some things I'd like to be able to keep an eye on in it, and I'm planning a series of videos about them. So stick around and see an old cheapskate trying to learn new tricks. Hi, I'm Gary. I'm a retired engineer who makes videos about technology stuff that interests me, usually from a user point of view. Do you know what a smart home is? I'll read you one of the definitions I found online. A smart home means your home has a smart home system that connects with your appliances to automate specific tasks and is typically remote controlled. You can use a smart home system to program your sprinklers, set and monitor your home security system and cameras, or control appliances like your refrigerator or air conditioning and heating. If you really want all of that, you probably need to look somewhere else, because I'm not particularly interested in controlling my refrigerator remotely. Most of those features have doubtful utility to me, and I'm certainly not going to pay for them. I'm a dinosaur, remember? I live in an almost 50-year-old house where my only control other than light switches is the programmable thermostat in the hallway that lets me choose between heating and cooling. And I've been just fine with that. But I am planning to do some things in my house that border on smart home technology. And this video is intended to explain why, what they are, and how I'm intending to go about them. What I expect you will learn from this is perhaps the right way to plan a project and the wrong way to go about implementing it. So be sure to subscribe if you haven't, and click that notification bell for future videos, because this may take a while, and you won't want to miss the entertainment. Let's start with the why. Why would an 80-year-old guy choose to wade into unfamiliar technical territory in pursuit of information he's managed without for decades? 3 reasons, really. First, it's not totally unfamiliar. I worked as an instrumentation and measurement engineer for years, and as a project engineer for a testing lab. Second, the prospect of doing this has stirred up interest from years ago, and I'm simply having fun pursuing it, with more fun to come. And I also hope to exercise my penchant for doing non-critical things as cheaply as possible. Third, and most importantly, there actually are some technical reasons. We finally air-conditioned our house a couple of years ago, and the furnace also had to be replaced as part of that upgrade. I had doubts about the sizing of both of those, even though the new system seems to work okay. There are variations in temperature, and thus in comfort level around the house, that seem more noticeable than they were before. And of course our energy use is higher now that we have air conditioning. Those concerns pretty well define the what part as well, which constitute what an engineer would call the requirements phase of this project. I want to be able to measure and record the temperature at various locations in my house over time, as well as to compare them to outside conditions. And I want to be able to monitor and record power and energy use over time as well, particularly for the heating and cooling system. This project may or may not evolve beyond those goals as time goes on. For example, can I actually do anything about the temperature distribution issue? But for now, those are the major requirements. This is where it starts to get technically interesting, or maybe complicated, would be a more accurate description. Let's start by talking about measuring temperature. There are a lot of ways to measure temperature, even if you limit them to the range where humans can live, like my house. For example, I have mercury thermometers, bimetal dial thermometers, probe thermometers, infrared thermometers, a temperature probe for a multimeter, and even a thermal camera. They all measure temperature, but I need the measurements to be recorded automatically. For my purposes, the measurements don't have to be incredibly accurate, but they do need to be consistent, meaning stable over fairly long times, like days or even months. Also, they need to be comparable, meaning that if the temperatures in 2 different locations measure the same, they should be the same. And conversely, if they measure 5 degrees apart, they really should be that different. Otherwise, drawing conclusions from the measurements is useless. Back in the Jurassic era, when I was a test engineer, the three most basic ways to measure temperature electronically were thermistors, thermocouples, and resistance temperature devices, called RTDs. Thermistors and RTDs are sensors whose resistance varies with temperature in a predictable manner, while thermocouples actually generate a voltage that varies with temperature. All of these devices have at least a couple things in common. They're all analog devices. Their change with temperature is a continuous variable that can easily be turned into a voltage to measure. However, none of them is perfectly linear. The relationship between their temperature and their resistance or voltage output is not a straight line. But they can all be corrected, at least theoretically, to within a degree or so over my range of interest, either by electronic circuitry, like this, or by digital calculations. When my house was built back in the late 1970s, I actually installed a bunch of thermistor sensors throughout the house, and then programmed the data acquisition system for them using a computer built from kits, along with an analog to digital converter board, also built from a kit. I recently stumbled across the software I wrote or modified for that, and I was amazed at the dozens of pages of basic and assembly language code and calculations it took to make it work. I threw all that away. In fact, it appears that the thermistors and their wiring are still lurking in my house. You can actually see one of them next to the thermostat in that earlier video clip. So am I going to use them? No, I'm not. I'm no longer sure of all their locations. I can't tell which is which, and there's no way to calibrate them now without pulling them out of the walls. Not to mention that they come into my electronics area to this rat's nest of an unlabeled terminal strip. But thermistors are dirt cheap and easy to use. All you need is a resistor for a voltage divider and an A to D converter. So why not use them? Because technology has changed radically in 40+ years, that's why. Nowadays, there are inexpensive little devices that do the conversion, generate a digital output, and send it over some kind of interface to a computing device. Here's one example that is in fact the sensor I hope to use. It's a DS18B20 packaged as a waterproof probe, and I bought a batch of them from Amazon for about $2 each. They will measure from -55 to +125 degrees Celsius, with a claimed accuracy of plus or minus half a degree Celsius, which is certainly close enough for my use. No calibration, no adjustment, just apply 5 volts or so and out comes the digital data on a serial bus. We'll talk about where that goes in a minute. Let me go on to measuring power and energy. My house is heated with electricity, so we're talking about power values in the tens of kilowatts in a 240-volt system. This requires a certain amount of care to avoid frying oneself. I'm certainly not going to go randomly sticking measurement devices in this system without giving a lot of emphasis to safety, and you shouldn't either. At first glance, measuring power and energy should be easy. Power is basically the product of voltage and current. So you measure the current and measure the voltage and multiply them, right? But you need a way to measure the current, preferably one that doesn't involve disconnecting wires and inserting things in 240-volt circuits where they can go bang. No problem, we'll just use a current transformer. So before I thought this through, I bought a couple of these so-called split-core current transformers. You clamp them around the wire carrying the current of interest, and they produce a small, like 1-volt output signal that can be connected to an analog to digital converter on some computing device. Presto, you measure the current. I checked them with a voltmeter, they work. It sounded good. Voltage is even easier. You can measure the voltage with a meter and assume it stays that value forever, which isn't actually a terrible assumption for a modern electrical power system. It might even be good enough for my purposes. Or you can simply step down the voltage by a known ratio with a transformer or some kind of voltage divider and measure its output. Multiply those two things together and there's your power. That actually works fine if you're doing this with a voltmeter or an amp meter, or with a kilowatt meter like this one, because they will show you an average value over some measurement time. Doesn't really work if you're doing single-point digital conversions to be able to record the values over time, because the values are not averages, and the voltage and current probably won't even be measured at the same time. We're talking alternating current here, that varies in a sinusoidal fashion at 50 or 60 times per second. If you measure the current and voltage even a millisecond or two apart, you will get a significant error. So if I do it this way, I have to make a lot of measurements quickly over the complete cycle, and then average them in software, and also account for the fact that there may be a phase difference between the current and voltage if the electrical load isn't purely resistance. I'm not getting into that, but take my word for it, it's work. And at my age, I am not interested in getting into serious computer programming again just to multiply two numbers in a complicated fashion. So the simple hardware approach is a no-go. Fortunately for my laziness and my cheapness, there seems to be a modern solution to this problem. This little gadget is called a PZEM004T energy monitor, and it's less than $10 on AliExpress, including this 100 amp current transformer. You connect the transformer and the line voltage to its inputs, and it does all the work, giving you digital output values for voltage, current, power, and energy, along with power factor and frequency, all over a serial data interface. Problem solved, I hope. That brings me to the third key component of this project. You may have noticed me referring to a computing device as the target for this data. What kind of computing device are we talking about? These sensors are not intended to connect directly to an ordinary personal computer. It would take some complex interfacing and equally complex programming to make that work. Did I mention I'm lazy? So the obvious choice is to use one of the common little microcomputers that are designed specifically for this type of real-world interfacing. The Raspberry Pi would do the job handily, for example. But it's not only overkill, it involves a bigger software learning curve than I want. And it isn't really cheap. So in the interest of both laziness and cheapness, I'm going to use an Arduino microcontroller, which has all the right interface hardware for these sensors, and also a huge amount of user-developed software that's free for the taking and the modifying. I splurged and bought this one, which is a more recent Uno R4 minimum model, for the grand sum of $22 on Amazon. Then I later discovered that I could buy a clone of the earlier Arduino Uno R3 for as little as $4 on AliExpress. So I did that too as a backup possibility. You may have realized by now that all this discussion has been sort of hypothetical. I have bought all this hardware, and I have verified that I can program the Arduino with its excellent and free integrated development environment on a PC. I've even gone so far as to read the output from a digital temperature and humidity sensor, like this. But none of this is yet installed in my house and working. So this is like baby steps for this project. That's largely because the last 6 weeks has been like walking into a new universe, where everything you learn promptly gets modified by something new. And the next thing you know, you're not really quite sure what the best way to go really is. For example, the temperature sensors are simple from the user point of view, but they interface to a one-wire bus that's best connected from point to point, rather than in a star arrangement. I need measurements at points more than 50 feet apart. Will the signals tolerate being carried around on cables strung out that far? What kind of cables will work? Will I wind up needing to multiplex them or maybe transmit them over Wi-Fi instead? And the same kind of questions apply to the power measurements, some of which need to be made out in my garage, even further away. Will I have to change my whole approach and go to some kind of distributed network? There are so many possibilities, it's actually been hard to just decide and get started. So I hope you'll stick with me as I try to find out what works best for bringing the IQ of my dumb house up from idiot level to imbecile, and maybe me along with it. If you enjoyed the video, please leave a like for it. And as always, thank you for watching.